In this video, we're going to talk about the topic of optimization, and we're going to learn how to use calculus to actually solve optimization problems. So, optimization is a branch of mathematics that basically centers around the idea of finding maximum or minimum values of a particular function according to certain constraints that we may set on it. So, it is sort of an abstract field, but I will show you some applications of it through examples, and that will give you a better intuition of what it is all about. So in this, the first example that I'm going to show you is the following. Imagine that you have an area in some field, and you want to build a fence around it. So basically, let's say you have a farm, and you want to either put some cattle in it, or maybe grow a series of crops or different things in there, but you only have a limited amount of fence that you can use. So essentially, let's say the width of that fence is denoted by x, and the length, or the vertical length, is going to be y. And let's say that for the sake of argument, you have a maximum of 2,000 meters of fence with which you can actually build this. So a question you may ask is, how can you build this? So what dimensions x and y can you use to actually maximize the area that you surround with this amount of fence? So how can we formulate a mathematical problem with this in which we can use calculus to solve it? Well, the first thing we need to do is establish a relationship between the variables. So what is the thing that we're trying to maximize here? It is the area. So we're trying to maximize the area, and the area in this case is going to be a function of x and y. So the area of the rectangle is going to be x times y. So this is our function of the area. So obviously you notice there are two variables in here, so this is a function of two variables, but if we want to use the tools from calculus we have learned so far, we will need to reduce this to a function of a single variable. So how are we going to do that? Well, so far we have two variables, but only one equation to work with. So obviously, if you have ever solved simultaneous equations, you will know that this will not give you any solutions. You cannot solve it because you don't have the same number of equations and variables to solve for. So we need another equation to balance this out. And that equation is going to call the constraint. So the constraint is essentially a condition that you set such that the variables that you're going to involve in your function are related in some way. So in this case, our constraint would be that the total perimeter must be equal to 2,000 meters, because that is how much fence we have to work with here. So we know that the perimeter is going to be 2 times x, because we have this amount like right here, and we have 2 times y because we have a y length of fence on this side and this side. So 2x plus 2y should be equal to 2,000. And we can usually simplify this, so that means that x plus y needs to be equal to 1,000. So this is going to be your second equation. And now that you have two equations and two variables, you can actually proceed and solve this. So the first thing we need to do is we need to reduce to function of one variable. Reduce to function of one variable. So what we can do is we can set y, so we can solve for this in terms of y so that we can substitute back in here. So if we use the second equation, we have y equals to 1,000 minus x. So that is our condition. And if we substitute this back into the first equation, which is our function, we're going to get x times 1,000 minus x. And if we expand this out, that's going to be 1,000 x minus x squared. So if you notice, now we have a function of a single variable. That's good. Now we want to find the maximum. So we want to find the maximum of a. And to do that, we're going to take the first derivative. So dA with respect to dx is going to be what? It's going to be 1000 minus 2x. So this is going to be our condition. Now, to find the stationary point, that can be either a maximum or minimum, we need to set the derivative equal to 0 and then solve for the points of x that will make that 0. So in this case, we're going to end up with x equals to 500. So x equals 500 meters. Now, how can we check whether this is actually a maximum or minimum? Well, we're just going to take the second derivative. So d squared a over dx squared. And so we're going to differentiate this function again. This constant will become 0 and this will become minus 2. So this is minus 2 and this is less than 0. And if you remember from the previous videos we made on the second derivative, you will know that this represents a maximum point. A maximum point. And that makes sense because our function here is a quadratic. So it is just a parabolic function, which means that it will only have one turning point. And in this case, it will be concave down because we have this leading minus 1 attached to the x squared term. Okay, that's good. We have proved that that's a maximum point and it occurs at this point. In fact, it occurs for all points of x. So we know that this is going to be the value that maximizes it. So what do we do now? Well, we can substitute this back into y. And if we put 500 in here, that's going to give us y is also 500 meters. Now, it doesn't necessarily need to be both of them the same length, but it just so happens in this example that they're both the same. So that is quite a neat property in this case. So our original function, so what is going to be the maximum value of a now? Well, the maximum value of a is going to be equal to 500 times 500, which will make this 500 squared, and that's going to be 250,000 meters squared. So this is going to be the maximum area we can actually create using that 2,000 meters of fence. Of course, we could easily choose to make a different shape. It doesn't have to be a rectangle. We could do a circular kind of area, but in this case, we just focus on the rectangle. And it's a really interesting thing. Optimization is all about this. It's all about finding optimum values in a function. And here we found that for this particular case, the best thing that we can build is actually a square area, which is a bit of a coincidence, but in general, this is what you can do with optimization. And I'm going to show you a similar example, but now we're going to try to maximize the amount of light that goes through a window given limited materials, because in the real world, if you think about it, you always have limited resources to work with, but you need to find the best way to make use of them, and the best way to make use of them needs to be carefully calculated. And this is why the branch of optimization is so crucial to a lot of fields, including engineering and economics. So in this second example, we're going to have a window that consists of a rectangle, and then it has a semicircle at the top. Semicircle at the top. So I'm going to redraw this a little bit because I want to make it fairly symmetrical. So we have rectangle here. And you're going to assume that this is a semicircle. So this length here we're going to call S. That's the arc length here. This semicircle is going to have radius R. And then this is going to be the height of the rectangle. And this here is going to be the width. Now, what do you notice about the width? Well, the width is actually going to be 2 times R because it will correspond to the diameter of that semicircle. So we can reduce variables by just making this a function of R. Alright, so what's the question? We need to maximize the amount of light that goes through the window, and obviously the more area you have, the more light that is going to come through. So let's say, for the sake of argument, that you have a limited perimeter of 20 meters. So this is how much you have in total. So what is the perimeter going to be like? Well, the perimeter is going to be the sum of all these sides. So that's how you're going to build your constraint. Your constraint is going to be built as follows. You're going to add 2r plus 2 times h, because you have two sides here that are length h, and then you're going to add to that the arc length of the semicircle s. And if you remember, the circumference of a circle is 2 pi r, so half of that is going to be pi r. So this is going to be pi r here. All of this should be equal to 20. So that's how much perimeter we have to work with in this case. Now, what is the total amount of area that you need to have? Well, the total amount of area that you want to have in this case is going to be what? It's going to be the area of this rectangle, which is going to be 2r times h, plus the area of the semicircle, so that's going to be half of pi times r squared. So this is your function. This is what you're going to be maximizing. So we're going to maximize this area. So how do we do that? Well, first of all, we need to try to replace this by a function of a single variable. So we can use the constraint function to find a relationship between h and r that is explicit. So in this case, what I'm going to do is I'm going to solve for h. So if we look at the constraint equation, we're going to have 2h equals to 20 minus 2 plus pi times r. So this is just factorizing the r outside. And then h is going to become 10 minus 2 plus pi over 2r. So what are we going to do with this? Well, we're going to replace this back into the equation for the area. So that's going to be area as a function of r is going to be 2r times 10 to the minus 2 plus pi 2r. And the reason I'm leaving this 2 plus pi is because I want to have an exact numbers for now. And once we have to calculate the area, I'm going to start approximating this using decimals. So, and this is going to be plus half of pi r squared. Alright, so next step to optimize this is we want to get the derivative of dA with respect to r. So first derivative is going to be this is going to be 20 minus, actually I should just expand this out first so that it's easier to work with. So let's expand this out. This is going to become 20r minus 2 plus pi r squared plus half pi r squared. Now that we have that, let's find the derivative. So this should make it easier. dA over dr is going to be equal to 20 minus 2 times 2 plus pi r plus pi r. So this is our derivative, and we're going to set this equal to 0 because we want to find the maximum, or the value of r that will give us a maximum area. So we're going to do some rearranging here. So this is going to become 20 minus 4r minus 2 pi r plus pi r equals to 0. So once we rearrange this, this is going to give us the value r equals 20 over 4 plus pi. And this is approximately equal to 2.8. So this would be 2.8 meters. Alright, now that we have an estimate value for r, we can actually find the value of h. So h is going to be the formula that we had before, which is this. So let's put 2.8 in here, and surprisingly that gives us a value that is very, very close to 2.8 as well. Surprisingly, that's the same. Alright, so what are going to be the dimensions of the window? Well, we know what the height of the window needs to be, of the rectangular section, needs to be 2.8 meters, and the radius needs to be 2.8 meters. And this implies that the width of the window, which is 2 times r, needs to be around 5.6 meters. Now, with this kind of optimization problems, rarely will you find exact numbers, so it's important, you will have to use approximate numbers and decimals in most cases, so don't worry about this. Now, what is going to be the maximum area based on these calculations that we just made? Well, the maximum area, if we plug r back into here, that's going to be maximum area is going to be around 28 meters squared. So that's going to be your final answer. And in the next video, we're going to keep doing some examples on optimization. You can actually apply not just to these types of two-dimensional problems, but you can actually apply to three-dimensional problems. And there are very interesting applications of optimization and calculus to solving these types of problems, which are really important in a lot of fields. So that's what we're going to be doing next.